Okay, we're going to be continuing our journey into organic chemistry by talking about some different functional groups. Now, hopefully your memorizing of the different functional groups is going well. Today we're going to talk about alcohols, thiols, ethers, aldehydes, and ketones. And so it's really important to make sure that you know how to identify these different functional groups because we name them a little bit differently based on which functional group it is. It also has different properties, and so you may have to compare the properties of each. And so if you're looking for what classifies something as an alcohol or phenol, thiol, or ether, for an alcohol, you're going to look for a hydroxyl group. So like hydroxide is OH minus 1. Hydroxyl is a side group, it's not really a side chain because it's like a main functional group of an alcohol. So if you see anything with OH, then with only OH, not the carboxylic acid where you've got C double bonded to an O and then an OH, I mean just an OH, nothing else attached to that carbon, that's a hydroxyl group, and that is an alcohol. You can also have this happen off a benzene ring, and we call that a phenol. If you have an SH group, and if we look at the periodic table, we see that oxygen is right on top of sulfur, and so your alcohols and your thiols are going to be named very similarly. They will have a little bit different properties because oxygen partakes in hydrogen bonding, but sulfur does not, and so you'll have some differences there. But as far as like the overall structures and the overall naming of them, they're going to be pretty similar. And so you'll call that a thiol, and then you'll also have an ether. So an ether is kind of like an alcohol, but instead of an H, we have another carbon group. And so an ether is, I always remembered an ether by looking at it like this. It kind of looks like a bat flying with wings, and I don't know why, for some reason that made me think of an ether. No idea. But you know that it is going to be bent because this oxygen will have these two lone pairs hanging out up here like it does in water, so you're going to get a bend in it there, so you're going to have a bent structure in your ether. But for some reason to me that looks like something flying, and I guess that helped me remember ether. Maybe because ether is a volatile gas and so it flies through the air like something that would fly. Hopefully that will help you with that. And so here are some of the different ball and stick models. We can see that oxygen is represented in the red, sulfur is represented in the yellow, and you do get that bent structure around all of your oxygens and sulfurs because they have the same valence electrons in the same family. So we're going to start with alcohol. So naming alcohol, replace the E with all. And so if you're thinking about turning methane into an alcohol, we would add an OH to that methane, and we would call it methanol. It has a common name of methyl alcohol. Common names here are not quite as different as some of the other common names we're going to see, but you may hear someone say methyl alcohol or ethyl alcohol. You may need to know what that means depending on where you're working, and that's just the common lingo they use. Typically, people are pretty familiar with methanol and ethanol, so you're probably fine with using the IUPAC names. So let's go ahead and give it a practice. So dive right in. So pause and see if you can name this alcohol. Alright, so the first thing we're going to do to name the alcohol is the same thing we do to name alkanes and alkenes and alkynes, is to find your longest carbon chain. And so we have to isolate our longest carbon chain. We have, if I start here, counting 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, or 1, 2, 3. It looks like 6 is the winner, depending on if I start here or if I start here, it doesn't matter. So I'm going to put a ring around it on my main chain. Except this time, the ending is not going to be ane for alkane, because this is not the functional group of only single bonds to carbon. This is a functional group of an alcohol. And so if I'm counting 1, 2, 3, 4, 5, 6 main carbons in my main chain, I know I'm going to be hex. And if I have this, so it would be hexane, that would be the main chain. But in order to name an alcohol, we take off the E and we add an OL. And so I'm going to highlight my alcohol group, and I'm going to call it OL here. And so this is hexanol. If it had a double bond in it, you would put an E here, so it would be hexanol, but this is a single bond, starts from an alkane, so we would say hexanol. And then we do have a side chain hanging out. We're going to address that later, but first you have to tell me, and backing up in this name, well, there's a special group here. And with hexane, you have 6 carbons, so there's lots of different possibilities for where the OH could be. You have to tell me which carbon it's on. And with your functional group, it gets the highest priority of carbon numbering. And so we can number our carbons in a few ways. And so looking at the numbering of our carbons here, we can say 1, 2, 3, 4, 5, and 6, moving from left to right, or we can say 1, 2, 3, 4, 5, 6, moving from right to left. And as you can see, our numbering on the top is a lower number, and so my alcohol is going to get a lower number of 2. So we'll say 2-hexanol. Where is the alcohol? It's on carbon 2. And now we do have another side chain that needs to be addressed, which is no big deal. We'll do it how we've always done it. And so we have a side chain. A side chain is a methyl group because it's 1 carbon. And so where is our methyl? Now remember, when we start numbering, we have to keep the same numbering pattern. We can't say, oh, this is 2, because we've established this is 2. So it happens that our methyl may have to take a little bit of, it may have to be a little lower priority because the alcohol has to be higher than that. And so we're looking here, we're going to call this a 5-methyl 2, well, backing up, just give you a little space. 5-methyl 2-hexanol would be how we name this. If you're working through the slides, they kind of take you through this whole process. All right, there we go. So give me another pause and try these now. Okay, so with our first one, let's label our main chain. Our main chain, we're doing green tonight. So main chain here, if you were to count that up, and we got 1, 2, 3, 4, 5. I know already I'm going to be numbering my carbons to give the OH the smallest number. And so this is a pentane, or was a pentane, but now it is a pentanol, because I've got an OH. Where is that hydroxyl? It's on the second carbon. And then I have my side chain, my methyl, hanging out on carbon 4. So this is 4-methyl 2-pentanol. Alright, now looking at this one down here, I don't really have a longest carbon chain because I've got a benzene ring, and so you should think, oh, that's something special. Remember, we talked about that. This is a phenol, and so as soon as you see that you've got a benzene ring with an OH, this is a phenol. And so you're going to tell me not where the OH is, because when we're thinking about benzene rings, you can rotate around, and we're always going to put the most important part on carbon number 1. So when you've got a ring, any carbon can be 1. And so this is going to be carbon 1, and I can either go clockwise or I can go counterclockwise, but I need to pick the way that gives my other group the least number carbon. And so I'm looking at that bromo over there, and I see the fastest way to get to the bromo is to go counterclockwise, so 1, 2, 3. And so I'm going to name this guy 3-bromophenol. And so this is just taking you through the same ideas. Cool. So alcohols and phenols. You may be aware that alcohols have a connection to health. We ferment glucose to make ethanol, and ethanol will get you drunk. It is an intoxicating product. It is making by fermentation of grain, sugar, starches. The yeasties will do that for you. And so we can also make ethanol by reacting ethene and water. And so you may remember the hydration reaction from the previous chapter. And so you can make ethanol like that too. So that would be like synthetic ethanol, ethanols that are made in a lab versus ethanols that are made for consumption. It may be a little bit different because in here we may find ethenes not quite as great of a byproduct if you don't react all of it into an alcohol. So here's another alcohol. This is a glycerol, and so it is a trihydroxy alcohol, and it's a really important compound, glycerols are. And so these 3 hydroxyls, they all have what kind of interactions with water? So with water comes along, these guys are going to be very attracted to water because if you look at this bonding, don't we have an H bonded to an O with a lone pair? So that's going to be hydrogen bonding, right? And so we're going to get hydrogen bonding 3 times in this group. So these polar OH groups have hydrogen bonding, and they're also very polar, and so it's going to have a very strong attraction to water molecules. So this side is going to be hydrophilic, and then this side, this long carbon side, would be hydrophobic. And so this is where we get into the idea of soaps and things that can trap dirt and oil, because you have one side of a molecule that's afraid of water, that's nonpolar, hydrophobic, and another side that's hydrophilic, that really likes water because it's polar. You'll see 1, 2, 3 propane trial in lotions, cosmetics, liquid soaps, those kinds of things. This is a small glycerol. You have very large ones that we use in larger, maybe soap type products. And then we have, here's ethylene glycol. So ethyl meaning 2 carbons. So ethylene glycol meaning this double alcohol here. It's antifreeze, and so we use ethylene glycol in antifreeze. It helps the water not be quite as high in boiling point or in freezing point. So it's very toxic. It's actually, because it has a sweet taste, people poison pets and children a lot with ethylene glycol, and it can be really dangerous. So make sure if you do have antifreeze, you really keep it away from little kids, you keep it away from your pets, because they'll be attracted to the flavor of it, and it's very, very toxic to them. You may have heard of BPA. Oh, this plastic bottle does not have BPA, or it's BPA free, or BPA leaching into my bottle, into my water. And so bisphenol, phenol, you know that word now, right? So going out into the world talking about things. Bisphenol A, meaning how many phenols? 2 phenols. So you see the 2 phenols here in the structure. So bisphenol A is it's used to make the plastic, including baby bottles. And so washing them with certain detergents can actually cause the BPA to leach out. So it's only the certain detergents, or if you're maybe washing something in really high temperatures, it disrupts this. It's a polymer. Meaning you get long chains of this to make the plastic. And so people don't want BPA in their stuff because certain soaps and high temperatures of washing. Like, do you want to wash your baby bottles in high temperatures? Yeah, because you want to kill the bacteria, but you can also leach the BPA out of the bottle into whatever's inside of the bottle, which goes into your baby's body, right? So you have to know about these things, and you should be able to research if your thing that you're using has this in it or not, and how to handle it. And maybe boiling the water for your baby bottles isn't the best if you have BPA in your baby bottles, right? So this is all really relevant information, and identifying these things as alcohols can kind of help tell you how it's going to behave. And so here's some more alcohols and phenols. Hopefully you can recognize the phenol groups here. Got a little phenol hanging out right here. One's right here, one's right here, and one is right here. If you want to go for a challenge, you could try to name these. They've got some some ethers hanging out, some aldehydes hanging out, some double bonds here, some alkenes, some serious branching going on. I'm not going to have you name something like this quite yet. But you can try it if you want. Alright, moving on to thiols. Like I said before, alcohols and thiols are going to be really similar. So instead of an OH group, you're going to have an SH group. So we're just going to call that a thiol group in our class. You may hear a mercapto group, like a mercaptan, because it traps mercury. But for right now, I'm going to let you get away with just knowing it's a thiol group instead of mercapto group. They often are really, really stinky, so your thiols are going to be your stinky substances, and so this is the thing that is responsible for the after odors of onions, garlic, found in some cheese, some stinky cheeses, some oysters. It's also found in skunk spray, thiols, and we put thiol into methane gas, and so if you've ever smelled gas, it's not the methane that has a smell. We insert a thiol compound into our gas lines so that you can detect if you have a gas leak, but methane itself doesn't have a smell, and so we actually put the smelly stuff in so you can tell whether or not you've got a gas leak, because people were dying with gas leaks and because they couldn't tell that the gas was leaking, and so we added this to the gas lines. And so if you see here, identifying your thiol is your little SH here, then they give us the name. So let's back this up and look at this. Where's my thiol? It's on carbon number 1, so they've established this is carbon number 1. I also have a butene. My butene means I have how many carbons? Right? 4, 1, 2, 3, 4. There are 4 carbons here. And I have a double bond because it's an ene. Where's the double bond? On carbon 2. So this is carbon 1 with the thiol. Carbon 2 is where I start my double bond between carbons 2 and 3. And then this is trans, which means that the important groups are on opposite sides of the double bond. And so you can back yourself from a name into a compound and vice versa. I would always, always, always go through that if you're studying to make sure you know where they're getting the name from if you're given both the structure and the name as an example. So how do we name thiols? We name thiol just like we would name an alcohol. Instead of putting an "all" at the end, we're actually just going to leave the whole name and say thiol. So methane becomes methane thiol. Ethane becomes ethane thiol. 2-butane. Butane becomes butane thiol, and here we have to tell where the thiol is, because once you get more carbons, you got to tell where the thiol is, and so the thiol is on carbon 2, so we say 2-butane thiol. It's not butanethiol or anything, just say butane thiol, merge the words together, taking out the space in between, makes it really simple. There are obviously very confusing common names for this group, but we're not going to worry about those. And so methane thiol, really simple ones, oysters and cheese. Then you got onions, 1-propane thiol. So how many carbons is that? That's 3 carbons for a propane. And where's my thiol? That's on carbon number 1. And then you got 2-propene, 1-thiol. So I have a thiol. Where is it? It's carbon number 1. And then I have propene, which is a double bond. Where's the double bond? On carbon number 2. So 1, 2. This is 2-propene, 1-thiol, the compound responsible for the smell of garlic. So another thing we can do with oxygen is make an ether. An ether contains an oxygen between 2 carbon groups that are either alkyl groups, meaning like regular meth, prop, bute, those kind of groups, or aromatic rings, meaning like benzenes. It has a bent structure, like water and alcohols do, and then it has a common name that gives the alkyl names of the attached groups followed by ether. So here we have dimethyl ether. So how many methyls are there? There's 2 of them. And they happen to be on either side of the ether. They have to be on either side of the ether because an ether is an oxygen in the middle of things. So if you see the word ether, you think, okay, oxygen in the middle. What's on the outside? 2 methyls. Okay, a methyl here, and that's how we name ethers. Most ethers, though, have common names. The common name is actually a lot easier than the IUPAC name for once. So we're going to be using the common names of ethers because the common name, to me, is more helpful. The common name uses the alkyl group or the aromatic group that's attached to the oxygen. We write them in alphabetical order, and then we write the word ether at the end. So if we look at an ether, we know, okay, I got oxygen in the middle. What's on either side of the oxygen? Well, a methyl group is on one side, and a propyl group is on the other, so I call it methyl propyl ether. And you will always put this in alphabetical order. It doesn't go in the order of the side which it's on, because if you're thinking about these in real life, you can flip them around and make this side on the left and that side on the right. So that doesn't really cause the naming. We always use alphabetical order for our names here. So let's try it. Ether is actually a really interesting compound used as an anesthetic. It will kind of put a patient to sleep. You have to be careful with ether because you can do harm to a patient with ether as well. But it was the first anesthetic putting patients to sleep while doing surgery was in ether. And so someone just, I guess I'm assuming accidentally discovered that that was a thing and then started using it to help their patients go through painful procedures. And so here are some ethers that are used in anesthetics. So we still have an ether groups, but we just reduce the volatility and flammability of the ether. So one problem with ether is that if you accidentally spill it, it's really volatile and it's really flammable. And so it's like spilling gasoline in your house, right? It's really, really easy to ignite. And then back in the day when we're using ethers, I'm talking like in the 1800s, 1900s, early 1900s, you probably got a lot of candlelight that you're doing your surgery by, and you really don't want that around the ether. So yeah. So go ahead and give me a pause and work through these compounds. So we're going to draw the structure. So you can draw a line structure, you can draw a condensed structure, you can draw a calculate or expanded structure if you want. I would suggest that you draw a line structure simply because it's the smallest structure. If you get to the point where you're familiar with line structures, it's going to make it a lot easier for you to work through, but you should also be able to do other structures from that. I will show you the line structure in all the videos, and then if you are interested in knowing what the condensed or expanded structure would look like, we can work through that as well. And so if you haven't already, pause and work through this and then unpause. So looking at our first one, 3-pentanol, and so breaking this down, do you have something special? Do you have a functional group? Well, look at the ending. I have an all. I have an alcohol. So that means I need to know, okay, that means I have an OH hanging off somewhere. Well, how many carbons is it hanging off of? 5 carbons. What kind of bonds do the carbons have? This ane right here means single bonds. So I'm dealing with 5 carbons, single bonded, and I have an OH hanging off. Where's the OH? It's on carbon 3. So where the OH is on carbon 3. So let's draw it. I got 5 carbons. 1, 2, 3, 4, 5. Every end and bend is a carbon. And I'm all single bonds, so no double bonds. Where's my hydroxyl? It's on carbon 3. So you can always pick whatever side you want to start numbering your carbons, but it's helpful if you just always pick the left, because then if you're building it, you build it however you want. So if we're looking at carbons, we've got carbon 1, 2, 3. So here is where my OH is going to be hanging off. And if you look, I can actually count either way to be carbon 3. So it's kind of cool. All right, what about ethanol? And so all means I got an OH. Eth means I got 2 carbons. Ane means I got single bonds. So I got 2 carbons, and I'll draw the condensed structure, or the expanded, actually it's 2 expanded. So 2 carbons here. And now if you only have 2 carbons, where is your hydroxyl group? It's always on carbon 1, right? Because if I put it here, it's carbon 1. If I put it here, also carbon 1. So it doesn't really matter where you put it. And then we just fill the rest in with hydrogens. And so that would be how we draw an expanded structure for something small. Maybe you want to do expanded, but if it's longer, probably want to do a line formula. All right, diethyl ether. So first of all, we see ether. Ether means O in the middle, like a little bat flying around. So I got an O in the middle. So I know I have an O in the middle. And now I need to know, well, what's on either side? Well, if I have ethyl means 2 carbons, right? And how many ethyls do I have? I have 2 ethyls. Well, that means there's 1 on either side. And so if I'm doing a condensed structure here, I have a CH2, CH3, that's an ethyl, 2 carbons. And here I would have a CH2, CH3. Remember, a CH3 is all for your outside, CH2 is on your insides. And so I have 2 diethyl ether here, 2 ethers on either side of my oxygen, making it an ether. Sorry, 2 ethyls on either side of my oxygen, making it an ether. Okay. So here are our structures. Properties of alcohol. You are familiar with alcohols. Hand sanitizers use alcohols, but they're flammable, so be careful with your hand sanitizer. It will catch on fire. There is a really dumb challenge done where people put hand sanitizer on their bodies and light it on fire. It's really not smart. Please don't do that. Alcohols are classified primary, secondary, tertiary. We're going to use this classification for alcohols. You can also use it for other things, but I want to take you through how to classify something as primary, secondary, or tertiary. It's going to affect the products that you make with different reactions. So if you're looking at these three different things, you're looking at how many groups are attached to the carbon that's bonded to the hydroxyl. So think about it like this. How many other groups is the hydroxyl sharing the carbon with? Your hydroxyl is going to be pulling electrons, right? Because it's that O is very electronegative. And so kind of how many electrons is it going to get? Like, it's going to pull from that carbon. So if that carbon has other things bonded to it to kind of help even it out, then it becomes a little less positive, and so it becomes a little less reactive. And so in organic chemistry, in full-blown organic chemistry, we talk about carbocations and their stability based on how many other things they have bonded to them that can kind of help them out if they become too positive. That all has to do with kind of what's going on in the structure, but primary, secondary, and tertiary alcohols definitely are examples of this happening. And so if I'm looking at a primary alcohol, so we would say one, use like a degree symbol to talk about primary. Primary alcohol there's one thing the alcohol has to share the carbon with. And so a primary alcohol has one alkyl group attached to the carbon that the alcohol is connected to. That means the other things are hydrogens, and the hydroxyl group does not consider the hydrogen as something it has to share the carbon with. It is not a threat. It only is sharing the carbon with this other CH3 over here. And so this is a primary alcohol where the hydroxyl is getting the carbon's attention, shared with only one other thing, so we call that primary. If you look over here at your secondary alcohol, we have an alcohol that is sharing the carbon with two alkyl groups. They're both methyl groups, but one could be a methyl, one could be an ethyl, doesn't matter. As long as you're looking at your carbon and you see two things that are not the OH hanging off of that same carbon, it's a secondary alcohol. And then your tertiary alcohol is your alcohol that has three things it's sharing the carbon's attentions with besides itself. And so you've got your alcohol connected to three things. Now, you're not looking at this carbon for counting how many things are around this carbon. You're looking only at the carbon that's attached to the hydroxyl. That is the only one that matters. So move one carbon in and count how many things are around that carbon. And then you'll get your primary, secondary, or tertiary behavior. And so go ahead and give it a check. Tell me if it's primary, secondary, tertiary. Go ahead and pause and do it. Alright, so looking here. So first you have to find your OH. So finding my OH, my hydroxyl group, it's right here. Look at the carbon that's attached to that hydroxyl. Now let's count how many non-hydrogen things, alkyl groups, are being attached to that carbon besides the hydroxyl. So you've got, on this side we have a CH3 that's a methyl group, and on this side we have a CH2CH3 that's an ethyl group. And so it looks like I have two non-hydrogen things attached to that carbon, so this is a secondary alcohol. All right, looking at the second one, here's my OH. It's attached to this carbon. This carbon is attached to two hydrogens and only one ethyl group on this side, so this is a primary alcohol. And if we're looking at this guy attached to this carbon has no hydrogens, which means all three of its bonds are being taken by alkyl groups. This is a tertiary alcohol. And so we talked about this a little bit before, but alcohols are, they have hydrogen bonding and they have a polarity, right? And they can hydrogen bond with water if they do not have really long carbon chains. And so we have to think that you've got two things going on here. Well, one side of an alcohol is superpolar, got hydrogen bonding abilities. The other side of the alcohol may be a very long carbon chain that's super nonpolar, and so eventually you're going to have one overpowering the other. If you have 1, 2, or 3 carbons, and so we're talking methanols, ethanols, and propanols, then your solubility in water is higher than you can solve in water. But if you are talking about butanols, pentanols, hexanols, heptanols, going on up, your solubility is going to decrease. And so you're looking at the nonpolar carbon chain, how long it is, and if you have 1 to 3 carbons, you can say it's going to dissolve, but if it's got 4 or more, probably not going to dissolve in water, because then your insoluble part, your nonpolar part, just starts to overpower this one little polar part, which is why your glycerols of the previous slide are so powerful, because they can hydrogen bond with water because they've got 3 hydroxyl groups, right? But this only has the 1 hydroxyl group. And so if you look here, as you get your butanols kind of on the edge, you're slightly soluble, but your pentanol totally insoluble. And so you can remember some of these. You need to know, though, that your only totally soluble alcohols are your first 3 carbons. So here's some information about hand sanitizers if you're interested. Phenols. So phenols are kind of soluble in water. They've got these 6 carbons in a ring here, and so they can dissolve in water. They can form hydrogen bonds here, and they can also react with water to form phenoxides, so like hydroxide, but a phenol, so phenoxide ions, and they're once used as antiseptics. And so they kind of have a little bit of what kind of properties does this look like, giving an H to water. You should think about that as being an acid reaction, right? And so this is an acid-base reaction with water, and so your phenol has acidic properties, right? This H is very acidic, meaning it will come off and leave you with a conjugate base of a phenoxide ion and make some hydronium for you. And it is a weak acid, right, because it has a double bond, or a back and forth reaction here. So go ahead and take a quick pause and tell me if it's soluble and why. So this big one is not soluble because it's got a long carbon chain. We got 1, 2, 3, 4, 5, 6 carbon chains. That's hexanol, not soluble. But I got my little ethanol down here, and you know ethanol is soluble in water, right? Yeah. So our next group is aldehydes and ketones. Aldehydes and ketones. These are also dealing with oxygen, but these are going to be double bonded with oxygen. So it's a little bit different than single bonds with oxygen. And so what they have are called a carbonyl group. So this carbon double bond to oxygen is called a carbonyl group. And there's a whole section of chemistry called carbonyl chemistry. You could spend whole semesters talking about just carbonyl interactions here. But it's a very polar double bond, right? Because carbon is not very electronegative, or not as electronegative, and oxygen is very electronegative. And so you can see I got a dipole here. I have my oxygen really pulling up those electrons, leaving my carbon very positive. So my carbon is now extremely positive and open to things that are negative to come and react with it. And you see here we get a trigonal planar geometry, which means it's flat, which means you can attack it from the top or the bottom. And so this just increases your reactivity. And so aldehydes and ketones have certain reactivities in organic chemistry, and they undergo certain reactions. And so looking at the difference here, in aldehyde, you have at least 1 hydrogen attached to that carbon. And so your carbonyl carbon has a hydrogen attached to it. Versus your ketone, you have no hydrogens attached to that carbon. You've got alkyl groups on either side. And so you should be memorizing the kind of formula for an aldehyde and a ketone. You got your carbonyl, and you got all carbons. You're a ketone. You got a carbonyl. You got 1 hydrogen hanging out. You're an aldehyde. I remember aldehyde has an H in it, and so I remember, oh, that's got to have a hydrogen on that carbonyl carbon. You can write an aldehyde group if you're talking about writing a condensed structure as CHO with the double bond is totally understood. You don't have to write the double bond out if you're writing an aldehyde. Aldehydes are always going to be on the end, right? Because you can't have something bonded to hydrogen. So if it's in the middle, it's definitely a ketone if you're looking at a carbon double bond. But if it's an aldehyde, it's got to be on the outside. But if you have a ketone, you can sometimes write CO. You can also just go ahead and show the double bond. Either way is appropriate for the condensed structures here. So naming aldehydes, you will just, using the IUPAC's name, you just change the E, so the ending, like we changed methane to methanol, you change it to al. So methanal would be the aldehyde with methane. But methanal is also called formaldehyde. And so here are those common names for the first 4 aldehydes. So you probably would need to know this if you're going to go into working into any lab area, even if you're working like a hospital lab, or if you are going into maybe nursing. I would know some of, like maybe like just formaldehyde and acetaldehyde, but formaldehyde should be familiar to you. That is just methanal, and so it's got 1 carbon, right? And then you've got some other common names, propion and butyr for 4, and they actually just put the word aldehyde on the end. So you may see those. I'm only going to require you to know the IUPAC names. And so naming aldehydes, you just really tell me how long the carbon chain is. So looking here, we got 1 carbon, methanol. We got 2 carbons, ethanol. We got 3, propanol and butanol. And you don't have to tell me where the aldehyde is, because guess where? It's on carbon 1. It's got to be on carbon 1, because the aldehyde cannot have anything attached to that little H right there, because it can only have 1 bond to it. So aldehydes are super easy to name. You know it's an aldehyde, put an AL on the end, call it a day. And so looking at this aldehyde, I'm gonna walk you through naming this one. And so I know it's an aldehyde. My longest carbon chain is 1, 2, 3, 4, 5. And you need to have your main chain have your functional group on it. Your functional group is not going to be on your side chain. So 1, 2, 3, 4, 5. So this is a pentanal, yeah, but it's got a side chain. So we can go ahead and we can name through that. And so we know we have a pentanal. And we have a methyl group hanging off of the second carbon, so that would be 2-methyl pentanal. Name it the same way we name all other kind of alkanes. For a ketone, we replace the E with -one. The common name your alkyl groups attached are named alphabetically, so you'll say like methyl, ethyl, ketone, just kind of like how we named ethers, right? So same kind of idea, except instead of the word ether, we just say ketone. But there is IUPAC names for ketones as well, and so for ketones, you're going to name just the whole thing, and you're going to tell me where the ketone is. Now, you only have to tell me where the ketone is if you have more than 4 carbons, because can a ketone be on carbon 1? No, because if you got a carbonyl on carbon 1, you're an aldehyde. So your ketone cannot ever be on carbon 1, so your smallest ketone, it has to be propanone. You can't have an ethanone, because then it would be ethanal. It would be an aldehyde. And so we got propanone, and then you have butanone. But once you get up to pentanone, you got to tell me where it is, because I could have it on carbon 2, or I could have it on carbon 3. And then you can also have cyclos. So this is a hexanone, meaning a 6 cyclohexanone. So it's 6 carbons in a circle. You have your ketone at carbon 1, and then we count down 1, 2, 3 for a little methyl group hanging off here. So let's go ahead and name this ketone. You may want to pause and work through this. Okay, so moving forward, you have your longest carbon chain, 1, 2, 3, 4, 5. So this is a pentanone. I've got a methyl hanging off of carbon 1, 2, 3, 4. So this will be 4 4-methyl 2-pentanone, because you'll have to tell me where that ketone is. Okay. your functional group always gets a smaller number. So, some of y'all may want to number your methyl here with 2. Now, methyl would love to have you number 2, but methyl doesn't take priority. Once your functional group is how we name our, we change the ending of our name to that functional group, so it takes priority. And so you'll have to tell me where that is. So anything above 5, you got to tell me where it is. But butanone, you don't have to tell me where it is. I know it's always on carbon 2. So aldehydes and ketones, they can make hydrogen bonds with water, but they can't make hydrogen bonds with themselves. But they do have an oxygen with double bond with a lone pair, so they can do hydrogen bonding with things that have that other part of hydrogen bonding. Remember, there are 2 parts to hydrogen bonds. And so they're very soluble when it's only 4 fewer carbons. But if you have more than 4, just the same thing with alcohols, then you get those carbon bonds are nonpolar and they start resisting the water. And so here you go with your solubility. Here again, just same as alcohol. So 1 through 3, definitely soluble. With ketones and aldehydes, you get 4 are soluble, and then 5 is slightly 6 is insoluble. So only 1 up from the alcohols. So some important aldehydes and ketones. Acetone is propanone. So that's a common name for propanone. Acetone, you've definitely used that. And formaldehyde, which is methanol. Here are some others. Benzaldehyde, which is almond, vanillin, and cinnamaldehyde, which is cinnamon. Oh no. So this should go here. This should go here. Oh, out of touch, sorry. Classify each as an aldehyde or ketone, so pause and give me a quick classification. So you should have your answers here. Remember, an aldehyde has a hydrogen on the end, close to that carbonyl group. A ketone's kind of centered, sandwiched in the middle. Go ahead and give me a quick pause and name them. Alright, so you should have here that the longest carbon chains for part A is hexa, 6 carbon chains. We say hexanone. We're going to have to tell me where the ketone is, but for right now, hexanone is your longest carbon chain, and then here your longest carbon chain is 4. Remember that Cl does not count as a carbon, so 4 here, so that's butanone. And now we're going to tell me where the carbons are, or the carbonyls are. For this butanone though, because it has a side chain, you have to tell me where the ketone is because I have to put it in relationship to the chlorine, to the chloro group. So you've got 2 hexanone, not 1, 2, 3, 4, 5, but 1, 2. We can count from either way, remember? And 2 butanone. And then now we have to name any other substituents. So this would be, if this is 2, then this is 3, 4, this is 4 chloro, 2 butanone. So your alcohols can do the same thing as alkanes. They can undergo combustion. So an alcohol combustion reaction is actually a little harder to balance sometimes because you have oxygens in the alcohol and then oxygens on here. So we kind of have oxygens on 2 sides in the reactant side, but they can burn. You know, if you've ever lit any alcohol on fire, there are drinks where people light them on fire, like flaming cocktails. You may have used on a flaming dessert like creme brulee. Typically they'll put a little bit of alcohol on the top just to burn it. So dehydration, what do you think that means? Oh no, this is all kinds of crazy. So this should be plus water over here. So ignore that. Okay. So dehydration means we get rid of water, right? When we're dehydrated, we don't have enough water, and so we dehydrate something. And a dehydration is the opposite of a hydration. So if you know a hydration from an alkene to an alcohol, you just dehydrate in the same way. And so you take your alcohol and you remove H2O, so we're going to be cutting it here, and we're going to be making a double bond between these 2 carbons. And then we have water as a product, right? And it happens in acid conditions, and you have to add heat to this one, so it's a little endothermic. You have to heat it with an acid catalyst as well. And so when we're talking about organic chemistry, we can also talk about oxidation and reduction. And oxidation and reduction happen in inorganic chemistry and by looking at charges, right? So like iron 2+ goes to iron 3+. That's losing electrons. That's oxidation. But we're not going to be counting electrons here with the organic compounds. And so I want you to think about oxidation and reduction as just bonds to oxygen. And so if your oxidation, if you have more oxygen bonds, then you were oxidized. If you have less oxygen bonds, then you're reduced. And so if you're looking at oxidation, then you need to have more bonds to oxygen. So where's my oxygen here? My oxygen is right here in this hydroxyl group. If I make more bonds to oxygen, I turn it from an alcohol into an aldehyde. If you have more bonds to oxygen, the oxygen is not going to hold on to that hydrogen. You're going to lose that hydrogen. And so we're actually losing that hydrogen in oxidation. So oxidation is like losing a bond to a hydrogen and gaining a bond to an oxygen. A reduction is the opposite. So primary alcohols will give us aldehydes, right? Because I don't have my carbonyl group with a hydrogen on the end. So what about an aldehyde? What if I made another bond to oxygen? So if I took this bond and I turned it into oxygen, then that would be a carboxylic acid. And so I would actually, this H would come back because it's super attracted to that O. You're not going to have just an O minus hanging out. It'll be attracted to an H, especially if you're in water. What if I have a secondary alcohol though? So if I have a secondary alcohol, right, then I will be losing my connection with this hydrogen to gain another connection to an oxygen here, and I'm going to become a ketone because I'm in the middle of at least two carbons. And so I'll become a ketone if you have a secondary alcohol. So it's really important to know what kind of alcohol you're talking about, because primary makes an aldehyde and then can go forth to make a carboxylic acid, and secondary can make a ketone. And if you have a tertiary alcohol, you can't oxidize it because there's no H on the carbon to lose. If you're oxidizing, you're creating more bonds to that H. I cannot create more bonds to this and lose a methyl group. The methyl group's not going to go anywhere. It's too stable. And so your tertiary alcohol will not oxidize. So here's some information about methanol poisoning. So if you drink methanol, it gets oxidized in your body and turns into formaldehyde, which turns into formic acid or methanoic acid in your body. So not great. Ethanol is oxidized in our body to form ethanal, acetaldehyde, and that then becomes oxidized to make carbon dioxide and water. So you can increase your carbon dioxide in your blood by drinking too much, which you know now can increase the acidity of your blood if you're not careful. And so if you oxidize a thiol, so here's how proteins make disulfide bonds. So disulfide meaning two sulfurs. If you are losing, so to oxidize, right, is to lose bonds to hydrogen. So losing a bond to hydrogen, if you have two thiols hanging out next to each other, you lose the hydrogen, they're going to bond with each other. So it's not necessarily an increase in bonds to oxygen, as it is also a decrease in bonds to hydrogen. So we're losing these two hydrogens right here, and they're going to bond, make a bond together to keep their 8. And so your hair has disulfide bonds, and you breaking down those bonds when you straighten it or when you chemically treat your hair can cause your hair to be either more curly or more straight depending on where it started. So here's some effects of alcohol in your body. The book really gets into like that, because if you're going into the nursing field, you're going into healthcare, you are going to probably and undoubtedly run into people who are drunk. And so just knowing the blood alcohol level, what that means, what typical behavior of the number of beers or glasses of wine, and what that blood alcohol indicates, and know that it's fairly small amounts if you're thinking of in 1 hour, and thinking about how you've maybe seen some people drink and how close maybe they've come to these levels of alcohol in their blood. So be really careful when at parties and drinking and things, and making sure you're not having too much. Now this is typical for a 150-pound person. So if you're larger or smaller, you know, depending on your metabolism, you could have more or less than this, but just make sure that maybe you're not getting quite up to these coma and death levels of alcohol poisoning. Alright, so last little bit we're going to talk about a tolerance test. So like say I have a compound and I don't know what it is, and I want to know if it is an aldehyde or if it's a ketone. Well, the tolerance test will tell me if it's an aldehyde or if it's a ketone, if I'm down to only those two options. Because the tolerance reagent, it has silver ions, and those silver ions, they oxidize aldehydes, but they don't oxidize ketones. So they actually turn aldehydes into acetic acids. And so you could think about this also like coming from an alcohol. You get a primary alcohol, you turn it to an aldehyde, you add a tolerance agent, and you get ethanoic acid. But you get a byproduct in a tolerance agent, you get a silver mirror look. And so if I kind of zoom in here, we get this, so if the ethanol is going to get oxidized, then what's going to happen to the silver ion? Right, it's going to get reduced. And so it's going to gain, the silver ion gains an electron to become silver metal, which is actually what we make mirrors out of, or we can make mirrors. We get this silver metal kind of shine in your in your test tube if you do a tolerance test, if you positive for an aldehyde. And then you have a Benedict's test. Benedict's reagent is kind of the same thing. Same idea is that the metal is going to get reduced. You have, they react with specific aldehydes that have a hydroxyl close to them. So look at how this thing is named. We have an al, which is an aldehyde, and it's a propanal. So there's 1, 2, 3 carbons in the chain. We know that it has to be on carbon 1. And then I have a hydroxy group. So like, which one wins? Would I call it an aldehyde or would I call it an alcohol? Obviously, we call it an aldehyde. That one wins, so it's on the end. And then I have a hydroxy group hanging off, so that's what I'll call this. And where is it? It's on carbon number 2. I put it with Benedict's reagent. I get a brick red solid coming out of it. And then it has turned my aldehyde into a carboxylic acid, but I still got it a hydroxy group. And so it's a very special case. Simple aldehydes and ketones will be negative. And so if you're thinking, maybe I have a more complicated hydroxy type thing going on, you can test this. But if you just have a normal, like formaldehyde, or a simple ketone, then your test is going to be negative. It's got to be an aldehyde with a hydroxyl group at the carbon adjacent. So like not down here, but like right next to it. And so you can see here's a Benedict's test. Here is a sugar, glucose, and glucose has an aldehyde end, and it has, see all these little hydroxyl groups hanging off right here? So it has an adjacent hydroxyl. And so the Benedict's test is great to test for glucose because glucose fits the criteria for aldehyde with a hydroxyl group adjacent. So you will start with your Benedict solution, which is blue. If you put it in the presence of glucose, it will make that brick red, this copper 1 oxide. So it's kind of like the marriage of organic and inorganic chemistry to do a test to see how much glucose is in a patient's system. You could actually isolate out how much copper 1 oxide you have, find the mass of it, and look at the molar ratios and molar masses and find out how much glucose the patient had in the sample that you're given. So we have some reactions, as I'm finishing up here, some reactions of aldehydes and ketones. Aldehydes and ketones are reduced by sodium borohydride. So sodium borohydride NaBH4 or hydrogen. And so the number of carbon-oxygen bonds is reduced by the addition of hydrogen or the loss of oxygen. So we know that that is reduction, loss of O, add of H. And a catalyst is needed for the addition of hydrogen to the carbonyl group. So let's just look at some of these. And so if we're looking here, we have propanal, okay, reacting with hydrogen under a platinum catalyst. So we know we're going to be kind of like adding the hydrogen to, where's the hydrogen going to add? So I got 2 hydrogens to add. One of them is going to add to the oxygen here, and then one of them is going to add to the carbon here. And so I'm reducing bonds to oxygen, and I'm adding bonds to hydrogen. So this is a reduction. and I'm going to make a primary alcohol. So if you take an aldehyde and add it to hydrogen, you're going to make a primary alcohol. If you take a ketone, you're going to do the same thing. We're going to make a hydrogen bond here and a hydrogen bond here, and I've made myself a secondary alcohol. And this can be done in nickel, platinum, or palladium, in anyone, but both reacting with hydrogen gas. So go ahead and why don't you try. Let's try to oxidize these things and see how it goes. Here's a sample we're going to oxidize. We're going to oxidize this sample here, and then try to guess which of the following A, B, C, or D is going to be your product. All right. So the correct answer here is B. And so if I am looking at an alcohol, it's just a primary, secondary, tertiary alcohol. So first, let's just review what would happen if we had these. If you have a primary alcohol and you are going to add more oxygen bonds, you make an aldehyde, yeah? If you have a secondary alcohol, you get an alcohol that's got a little more friends or competition there, you're going to make a ketone. And if you have a tertiary alcohol, you try to oxidize it, you get no reaction. Nothing is going to happen here. If you keep going with an aldehyde, what do you make? Right, you make a carboxylic acid. So we can keep oxidizing all the way to carboxylic acids from primary alcohols. And so this is a secondary alcohol because my carbon attached to the hydroxyl group has 2 other carbons attached to it. And so I'm going to make a ketone, take away your H, add a double bond. That's your oxidation. So we're making a ketone here. So go ahead and do 2-propanol. Tell me what happens when it undergoes oxidation and what happens when it undergoes dehydration. So we first need to draw out 2-propanol. Again, pause if you haven't done this already and do it first before you draw it out. So let's draw out 2-propanol. So we have an OH for sure. Where's the OH? On carbon 2. And